Bismillahirrahmanirrahim. Today's topic is about combination of two important aspects of wireless communication, MIMO and OFDM. So in this topic we will discuss about the combination of MIMO with OFDM. So this is the last topic for OFDM. So this is lecture number 33 of week number 14. So what is MIMO OFDM? MIMO stands for multiple input multiple output systems, which we discussed before, and OFDM is orthogonal frequency division multiplexing, which we discussed before. So MIMO OFDM is a combination of the best of the both worlds. It is combination of multiple input multiple output system and orthogonal frequency division multiplexing. So what are the advantages of combining these two technologies? Basically, MIMO OFDM converts a frequency selective MIMO channel into multiple parallel flat fading MIMO channels. So OFDM helps MIMO and MIMO helps OFDM. So MIMO OFDM significantly simplifies the baseband receiver processing by eliminating complex MIMO equalizer. So because of this, MIMO OFDM is the main current standard part of long-term evolution or 4G systems. So what is frequency selective MIMO channel? We know that frequency selective SISO channel is modeled as an FIR channel filter as follows. Yk is given by sum of L is equal to 0, L minus 1, HL x k minus 1 plus Nk. So Yk would be equal to H0 into Xk plus H1 into Xk minus 1 plus Nk. So this is the current symbol which has to be detected at the receiver. These are the pass symbols. So the combined effect causes inter-symbol interferences. Now similar to SISO, hence a MIMO frequency selective channel can be modeled as a MIMO FIR filter. So we have now Yk as a vector for MIMO FIR filter, which is sum of L is equal to 0 to L minus 1, capital HL into X vector k minus L plus N dash k. So now we are applying basically a model of a frequency selective channel on MIMO. So we have received signal vector. This is the transmit signal vector from multiple transmit antennas. This is the channel matrix XHL, which corresponds to the Lth tab of frequency selective channel HL. So this is R into T matrix, depending upon how many receive antennas we have and how many transmit antennas we have. And this is a noise vector, which depends upon the number of receive antennas. So now if we expand this y vector, we get this thing yk is equal to this whole thing, in which this part is the transmit vector at time t, this part is the transmit vector at time t minus 1, and this part is the transmit vector at time k minus L plus 1. So this is a model of the frequency selective channel of the received signal vector. So now yk depends on the transmit vectors xk to xk minus 1 plus 1, which is previous transmit signal vector. Hence this is an L-tab frequency selective MIMO channel. So in a MIMO frequency selective channel, ISA or inter-symbol interference occurs between current and previous transmitted symbol vector. So in a MIMO OFDM system, one needs to perform the IDFT or IFFT operation at each transmit antennas. So if we have one chain, we have IFFT block and we have one transmit antenna, and this is the second transmit antenna, we have an IFFT block, and the third transmitter antenna, which is also having an IFFT block, and N transmit antennas, depending on how many transmit antennas we have. So this is basically MIMO, and on E transmit antenna we have OFDM. So we have combined MIMO with OFDM. So it means that we are transmitting multiple carrier frequencies on which the symbols are modulated through each antenna. So that is called MIMO OFDM. So this is the complete MIMO FDM transmit schematic. For example, here is given as 256 subcarriers and transmit antennas is equal to 4. So we have symbols, we have serial to parallel demultiplexer for transmit antennas. So basically we have the symbols are copied at each transmit antennas. So each chain of the antenna contains 256 subcarriers. So we have serial to parallel demux, we have parallel to serial combination, and we have a CP. and so we have the transmit antennas. So similarly here we have the other chain itself. So there is a endpoint I50 missing block here, so you can insert the endpoint I50 here at each transmit antennas. So we have CP at each transmit antenna, so we have multiple transmit antennas. So you can see this, that we have MIMO, and on each transmit antenna we have OFDM, so that is why it's called MIMO OFDM. So we can now see what happens at the MIMO FTM receiver. If you look at each chain at the receiver, depending on how many receive antennas we have, at each receive antenna, the CP is removed, there is serial to parallel DMOS, then there is an endpoint FFT, and then the output goes into MIMO detection. So MIMO detection is happening for each carrier at each RF chain of the receive antenna. So MIMO detection for the first subcarrier is performed here, MIMO detection for the second subcarrier is performed here, and for the last subcarrier is performed here. So if you see the outputs of this endpoint FFT, the first output goes to this block, the second output is going to this second block, and the third output is, or the last output is going to these blocks. So if we have 256 subcarriers, the first one will be going here, the second one would be going here, and the third and the last one will be going here. So at each MIMO detector, all the subcarriers are demultiplexed, or information is extracted from at each antenna for all the subcarriers on which symbols are being modulated. So this is the MIMO detection for the N subcarrier. The output goes to the parallel to serial conversion, and then all are there multiplexed together, and we have a serial stream of data coming out here, depending upon what was transmitted at the transmitter side. So for in this example, we have R is equal to 4. Hence, employing the MIMO FDM system, the advantage is the MIMO frequency selective channel can be converted into a set of parallel flat fading MIMO channels. So each MIMO channel at each antenna will have a Y0 vector is equal to H0 into X0. So recall that we have a frequency selective channel. The circular convolution, the time domain converts into simple multiplication of the frequency responses in the frequency domain. So Y0 is equal to H hat of 0, X dash of 0, Y dash 1 is equal to H tilde of 1 into H dash of 1. Similarly, Yn minus 1 would be H of n minus 1 to Xn minus 1. So these all are n parallel flat fading MIMO channels. So each MIMO channel will behave as a kind of a SISO channel in which there would be simple multiplication. So there would no interference between the subcarriers and between the taps. So in general, Yk would be equal to H dash of k to X dash of k. So this is the received vector corresponding to subcarrier k. This is the flat fading channel matrix corresponding to k. So it is not a frequency selective fading channel anymore. So this is t into 1 transmit vector corresponding to k. So each y0, y1 and yn minus 1 can be processed by a simple MIMO zero forcing receiver for detection of vectors x0, x1, xn minus 1. So what is that zero forcing detector? X at k would be equal to taking the pseudo inverse of this hk, because now we have a, as you recall from the MIMO lectures before, depending upon the transmit and receive vectors, normally we have more receive antennas compared to the transmit antennas. So we would have a pseudo inverse rather than simple inverse, which is valid only for square matrices. Pseudo inverse is given by this form, in which we have H Hermitian k into Hk inverse multiplied by H Hermitian k into the received signal vector at the subcarrier Yk. So MIMO zero forcing receiver basically gives you this H0, H1, H1 minus 1, and eventually it would give you the estimates at every frequency. So it basically converts flat fading channel matrices across all subcarriers. Thank you.